Hello, good morning, good afternoon. Implicit differentiation, okay? This is tricky. This you need to pay attention. I'm going to try to do my best. I don't think the examples I'm going to go through are that clearly explained in the book, and it may help if you pay attention to how I'm going to do particularly the second one, because I think the first one is straightforward enough. But for the second one, the way I like to think about it, it kind of gives you a framework, gives you like, oh, I've got to do this step, this step, this step, and it may make it easier for you. I don't think the book may necessarily make sense as it is written. But anyway, here we go, implicit differentiation. All right, you already know explicit differentiation, okay? Explicit differentiation is when your function that you're trying to differentiate, your y function, is just a function of x. There's only x's on the right side of the equal sign. So y equals 3x squared plus 2 log x plus cos square x. You know how to differentiate that. It may take you some time, but you can do that. That is explicit differentiation. There's only x's there, all right? Now, sometimes that's not going to be the case. Sometimes you're going to have a mixture of x's and y's on both sides of the equal sign, okay? So you may have x squared y cubed plus 3x equals 2y squared plus 2xy. I don't know, some crazy stuff like that. And rearranging it, making it y equals something, and so it will just take too long. It may not be possible, and that's when you have to use implicit differentiation. And I'm going to show you with a couple of examples how that works. And it can be tricky, all right? So fundamentally, this comes from the chain rule of differentiation, if you remember that. Now, there's no real need to sort of go back to it, but basically there's a couple of rules. There's two rules that you need to apply here, all right? Rule number one says that if I'm trying to differentiate, and you will find this in the book, but if I'm trying to differentiate y to a power relative to x, the answer is going to be n y to the minus 1 dy over dx, okay? So that's the first rule, and I am going to do the first example here, okay? So this is the rule. You can sort of box it up, whatever, but basically what it is here's my example. I've got x cubed plus x plus y cubed plus 3y equals 6. And I want to differentiate that. Maybe I'm trying to find a gradient, maybe I'm trying to find a norm, that sort of thing. Right, so what I'm going to do is just, I'm going to differentiate normally. You can differentiate this, but remember, I'm trying to differentiate with relative to x, or with respect to x. I'm trying to find dy over dx, okay? So, when I've got an x term, I just differentiate as normal, no issues, all right? So my x cubed is going to differentiate as 3x squared, the plus x differentiates plus 1. And when I got a y term, you're going to differentiate normally, so that's going to be plus 3y squared. But because it is a y term and we're trying to differentiate relative to x, you are going to write dy over dx next to it. And the next y term, the plus 3y, I differentiate normally. The derivative of 3y would be 3. But because it was a y term, I'm going to write dy over dx, and that equals 0 because the derivative of 6 is 0. once I've got that, and your derivative is going to be in terms of x and y, okay? It's going to be in terms of x and y, so don't worry about it. Now, what I am going to do here is I am going to take the 3x squared plus 1 to that side of the equation, and I am going to take common factor out dy over dx from these two terms here. So let me do this first. Dy over dx multiplies 3y squared plus 3, and that's going to equal, I take those two terms to the other side, minus 3x squared minus 1. And now, take that over to the side dividing, you've got your implicit derivative, so dy over dx is going to be minus 3x squared minus 1 over 3y squared plus 3. Okay, so that's the first example of implicit differentiation when you've got a mixture of x and y's. When you've only got an addition or a subtraction of x and y terms on their own. So you differentiate normally your x's, and when you're differentiating a y term, you add dy over dx next to it, and then you're just going to simplify and collect the like terms and sort of make dy over dx your independent term there. Okay? I hope that makes sense. That's, I think, relatively straightforward enough. I'm going to repeat it. Your x terms, you differentiate normally. Whenever you differentiate a y term, you tack on dy over dx after it and rearrange. Okay? Second example, trickier, because I don't think the book's making a very good job of it. So I'm going to explain it next. Okay, so the second rule that your book gives you for implicit differentiation, again, comes from the chain rule, and that means that when we're going to differentiate a product of x and y relative to x, what we're going to do is basically, if I got a product of x and y's, I'm going to differentiate twice. The first time I treat x as a constant, and the second time I treat y as a constant. So, if I'm treating x as a constant, I will leave the x there, and I will have my dy over dx. And the second time that I differentiate the same thing, if I treat y as a constant, I will have y, and then the bit that is not clear in the example is that I will have the derivative of the x expression, okay? I will have the derivative of the x expression there. Let's do the example and let me explain it, because I don't think the book does a very good job of it. So the expression we've got to differentiate is 4x y squared plus 6x squared over y. As you can see, I've got a product of x's and y's, and they are functions of y on top of that, and I need to differentiate, okay? So, like I said, I'm going to differentiate this first term here, and then we'll do the second, because I'm going to have to use this chain rule for the first product of x and y, and I'm going to have to do it again on the second time. So I'm going to end up with 4 terms, okay? So the first time, I said, I'm going to treat the x as if it was a constant, as if it was a number, and differentiate the y. So if x is a constant, I'm going to have 4x, differentiate the y, so that's 2y, and because I differentiated a y term, what do I need to do? I need to add the y over the x there. All right. And then I'm going to differentiate this same thing again, but this time I'm going to treat the y as if it was a constant, or the y squared as if it was a constant, and differentiate the x. So y squared is a constant, so 4y squared, and differentiate the x. The derivative of x is 1, so I just get that bit there. Okay? Then let's do the same thing with, so that's all of this is just the derivative of that, and let's do the same thing with that term there. We're going to differentiate 2 times. First time, consider x as a constant and differentiate the y. So if x squared was a constant, I will have 6x squared. Differentiate the y. That 1 over y is y to the minus 1. So that will be minus y squared. Remember, y to the minus 1 is minus y to the minus 2. And because I have differentiated a y term, I need to write the y over the x. And then plus, I'm going to differentiate the same thing again, but now I consider y to be a constant and I differentiate the x. So if y is a constant, I get 6 over y, the derivative of x squared is 2x, so that would have been 12x. So that is my implicit derivative. I would now collect like terms, get all my dy's over dx together. If this was equal to 0, which it may have been equal to 0, I may have only copied part of the question, but it doesn't matter. It doesn't matter. Let's just tidy up here. So I would have that dy over dx multiplies 8xy minus 6x squared over y squared, and then I've got plus 4y squared plus 12x over y. And as I said, if this was equal to something, I could take that to the other side and then divide like I did in the previous example. Okay, so this is where it gets trickier, as I think the book doesn't explain it very well, the example, but remember, you take each term, if you got a product of x and y, if you got multiplication of x and y, you're going to differentiate that twice. The first time, you consider x a constant, differentiate your y, and you write your dy over dx, and then plus, treat the y as a constant and differentiate the x. Hopefully, that made a bit more sense. But as usual, let me know if there are any questions, if you need any help, and we'll take it from there. Okay, I've also decided to do the third example, just to put everything together. I'm not interested in the substituting into finding actual numbers. I'm just more interested in the process of differentiating implicitly. So here, I think we need to find a gradient or something like that. In the question, this is example 3, but anyway, the important thing is to implicit differentiation, all right? So I'm going to have to differentiate both sides. Left-hand side, I've got a product of x and y. Because I've got a product of x and y, I'm going to do what we did before. First, treat x as a constant, differentiate the y, and then add the derivative of x considering y a constant. So let's go. First thing here, I'm going to consider x as a constant. So e to the 2x would be a constant. So I get e to the 2x, the derivative of log y is 1 over y, and because I have differentiated a y term, I need to add dy over the x. But I haven't finished, because now I need to consider log y a constant and differentiate e to the 2x, which I believe was there. And that's the left-hand side of the equation there. And now I need to differentiate as well the right-hand side. Well, differentiate x is just 1. When I differentiate a y term, I just do it normally, so it's 1. But because it's a y term, I need to tack on dy over dx, and the derivative of minus 2 is 0. So that is it, isn't it? Now I am going to bring all the dy over dx terms together on one side and the other one's there, and do that kind of stuff. So what I've got is dy over dx, which multiplies e to the 2x over y minus 1. That minus 1 is from bringing that over there, yeah, and that equals 1 minus 2e to the 2x log y. And then that is going to come here dividing, so dy over dx is 1 minus 2e to the 2x log y over e to the 2x over y minus 1. I'm wondering if that can be simplified, but I suspect not, because I've got the log y there. But anyway, that's it. And if I had a point, I could substitute it. If I knew the coordinates of the point, I could substitute it in to find the gradient of the line at that particular point. Anyway, interesting, isn't it? Exciting stuff. Let me know how you get on.